So our next speaker will be João Morais, who was until recently a PhD student in the Wireless Intelligence Lab at the Arizona State University, and did his PhD under the supervision of Professor Ahmed Al-Khatib, where he worked on the intersection of AI, localization, and software-defined radio networks. And he recently transitioned to NVIDIA, where he now works on the Aerial Research Cloud platform. And, well, for those who don't know, the Aerial Research Cloud platform, which we have heard already here this morning, is basically an L1 implementation from NVIDIA that runs on graphics cards from NVIDIA. And João will now talk about DeepMIMO, the community database and tool chain for ray tracing datasets. Thank you.
Oh, thank you. Okay. That way you can't interrupt me. I hope to be fast. Okay. Yes, like Robert said, I recently graduated. And during my PhD, I wrote version 4 of DeepMIMO. And DeepMIMO has become a part of AI RAN, particularly in the Data for AI work group, task group, which is part of work group 1, AI for RAN. And it is in that scope that this presentation came to be. So today I'm going to talk with you about DeepMIMO, the integration of DeepMIMO with OpenAirInterface, and some new things that it brings, hopefully, to the OpenAirInterface community. So, well, maybe let me see first, by show of hands, who has heard of ray tracing in the context of wireless channel modeling? Okay, great. My job is going to be easy. So you know it's important to simulate the channel realistically, even if you're not doing any machine learning. So great. So DeepMIMO's mission is to accelerate AI research in wireless by making ray tracing data easily accessible and easy to share at scale. And it has been rather successful at doing this, actually. Currently, it enabled more than 800 research papers across like 250 research groups. So it's going very well. This is DeepMIMO in a nutshell, version 4. On the top, you see ray tracing engines. On the bottom, you see simulation tools, possibly 5G stacks like OpenAirInterface. That's how we are going to integrate it. And DeepMIMO sits in the center, or sits in between them. What DeepMIMO does is act as a bridge, as a conversion tool, to allow you to mix and match both ray tracing engines, like Aerial Omniverse Digital Twin, Remcom Wireless Insight, or Schirner Ray Tracing, to simulation tools, like NeoRadium for InterDigital, the 5G Toolbox, and now OpenAirInterface. So let me go into a bit more detail of how DeepMIMO does this, which is rather simple. It has 4 components. One is the converter. First, it's essentially parsers. It parses the outputs of ray tracing simulations into one common format. And it does this in a single line of code. And when we write code to account for this format, to interface with this format, it becomes essentially interoperable across ray tracers, which is very useful. The second thing is, after we convert scenarios, so simulations from ray tracing, we load them into a database. We store them there. So that way, nobody else has to compute the same simulation again, which offers a lot of reproducibility. And some of those scenarios took more than a week to compute. So this way, you can download them in minutes and use them right away. So you also have some value there. And this database, at this point, has hundreds of scenarios and with multiple ray tracers. And this enables machine learning at scale. You can train across a wide range of deployments and see which ones work better or which ones work worse. It also enables, for the first time, comparing ray tracers. The third component, or second component, is the generator. So after we converted the scenario to a DeepMIMO scenario, and we can easily download it with a single line of code, now we can use that ray tracing output to generate wireless channels. And we can parameterize this generation. You see here some code to load the scenario, some code to load some default channel parameters. And here I'm configuring a certain base station and UE antenna sizes. and OFDM bandwidth. We can configure subcarrier pacings. What this allows you to do is essentially to sweep a wide range of parameters to do your simulations without recomputing your ray tracing simulation. So flexibility. It also enables you to change Doppler if you want, many configurations there. And reproducibility, because your channels are 100% determined by your scenario and by the parameters. So across those 800 papers, they were able to reproduce a lot of the previous results in previous papers. And lastly, it's the integrations. So after we generate some channels, we essentially export data. We export data to MATLAB, to Shiona, for you to continue the simulation in the tool that you like the most, that you're most comfortable with. Now, that's the basics of DeepMIMO. Now it's essentially some features that really provide some quality of life. The database, it's indexed by ray tracing parameters and by location. So if you want some scenarios from Austin, they exist. You can go there and you can get some of them. If you want some scenarios with only, or with diffractions, or with scattering, you can make sure to download those. And there's many more, like environments, indoor, outdoor. The ray tracing engine is also part of it. So this database can also be interfaced in code. So you can download scenarios directly in code. You can search the database directly in code. So here, for example, we set the maximum reflections to at least 5. So we are definitely computing enough rays. And if you want, it's not necessary, but after you ray trace the scenario, you can upload it to the database. So if you wrote a paper, maybe you want someone to use your ray tracing data, you can upload it also in one line of code. And if you do that, then you'll find a really nice dashboard to manage your submission to the DeepMIMO database. There's also many built-in tools, visualizations, things to empower you to inspect ray tracing data and see and analyze your channels with as little code as possible. So here, the data set is what we loaded. We have many matrices, in this case, the power, the delay, and the line of sight matrices. And we augmented slightly the NumPy matrix to support a plot function. So here we see 3 plots, a top view, a 2D view of the received power of every user. The base station is there at the corner. And you also see the propagation delay and whether the user is line of sight or not. It's hard to see, but in this case, there's more than 85,000 users connected to the base station, or pairs between base station and user. And there's many more matrices available. There's a power, phase, delays, angles of arrival and departure, azimuth and elevation, the interaction types, like reflections, diffractions, whether it was just line of sight. Interaction positions, we're going to see that in the next slide, some plots of interaction positions, and of course the positions of the users and the base stations. So some plots, more plots, you can plot the rays. One call as well. Here we see the exact places where the ray diffracted or where the ray scattered. We can also visualize the scene, and you can color the objects based on materials. You can also manage the scene. So for example, if you want to assign a velocity to a car, you can assign that velocity to a car, and the rays that interact with that object will have a Doppler shift associated with them when you compute the channels. And of course, you can overlay, and you can visualize things very easily. So in this case, it's a user moving across the city. This is in ASU campus. And ultimately, what DeepMIMO wanted to enable in the first place was an easy way for you to benchmark across many ray tracing data sets. So in these 25 lines of code, I do a little search of outdoor scenarios in the sub-6 GHz band, and I loop across those scenarios. I load them. If they don't exist, it will download them in the background. And I train 5 models. One that does channel compression, that uses the channels. One that does coverage prediction using the positions and the power. One that does CSI localization with the positions and the channels. And you can get the idea. Essentially, you can mix and match these matrices to train your models easily. And then it's a matter of splitting between test data and training data. You can use multiple scenarios. You can test in ones, train in others. But it becomes very easy, really. And then finally, one last feature that just happened recently, but we have been receiving a lot of positive feedback, is we have a database of publications. So all publications of DeepMIMO, so almost 800 at this point, are indexed in this database, and we index them by the task, so beam management, channel estimation, localization, and by the application, meaning, for example, virtual reality, cell-free, massive MIMO, security, UAVs. And you can mix and match these tags and find the papers that have used DeepMIMO datasets that you can reproduce. And you can also sort the database by number of citations or by the year. So everybody has been saying on those GitHub issues that it was very useful. So I'm glad. We are planning on adding another column to papers that have open source codes so that you know which papers can be reproduced easily. Yeah, there's a few more things like tutorials for beamforming and other uses of DeepMIMO. There's a lot of videos about that. There's an online visualizer, by the way. So you don't even have to touch code. You can go online and check your ray tracing scenario. We also support dynamic scenes where you ray trace multiple times, where you, in between scenes you change the positions of objects, and many more. This takes a while to change. Forum, roadmap, etc. Quite a few things here. Now, the news is the integration of the OpenAirInterface. The integration of OpenAirInterface, like I said, was actually motivated by the question of how to generate data that is standard compliant. And the plan was, let's connect the ray tracing scenarios that are relatively realistic channels to OpenAirInterface and run it in a simulation, like with our RFSim. Tomorrow, Bartosz is going to present the VRT sim, and that simulator essentially lets you move the user and in real time update your channels and to see the rays and to have the simulation run with those channels that you are updating. And essentially how the DeepMIMO integration in OpenAirInterface will work out is we're going to have a server that streams the channels depending on where the user is. The nice thing is all of this is pre-computed. So ray tracing is pre-computed, channels are pre-computed, so the simulator will be very interactive, and it should be very fun. There's two more, I think I have a few minutes. There's two more use cases that I really see them being useful for OpenAirInterface community. One is essentially testing the algorithms that you want to deploy before you deploy them with realistic channels. But also, well, not only that one, but also informing your deployment. So you can, for example, you are here in Austin, you already know how you're going to deploy your OpenAirInterface system. You can obtain the exact scene where the deployment is going to happen and ray trace that scene and have some clue on the coverage, have some clue on the angles of arrival that you are supposed to expect if you are doing localization. So hopefully that is useful, and hopefully also go back and understand what in the simulation led to differences, if there are any differences. And finally, of course, we couldn't live without this one. We're also open sourcing our ray tracing pipelines. What we use to populate that ray tracing database with 100 scenarios, we are making them available. There's a lot of things missing in this slide, but we're making them available. That way, hopefully, it's something as simple as a call to ray trace. You provide some coordinates of the scene, coordinates of the receivers and transmitters, and you provide some configurations of antennas, ray tracing simulations, and with one call and a lot of configurations, you ray trace in a particular ray tracer, which requires particular configurations, but we'll take care of that under the hood. And you can integrate that directly into OpenAirInterface. That's it for me. Thank you. Yeah. I was on time.
Very good, very good. Are there any questions here? Did I see one? Maybe Bob?
Hi, Bartosz here. I wanted to ask about, you said that you can change the velocity of an object after the data has been generated already. So how does that work?
Yeah, it's a simulation. Essentially, well, even in a static scene, you ray trace a single scene, let's say here, and you have users. You can simulate mobility by sampling users along the scene. Likewise, you can attribute velocities that are like instantaneous velocities. And you can consider those velocities as the user moves across the scene. So the object will not move in this static scene because you ray traced it like that. But the channels that you are computing can consider as if the object was moving. And as if the ray, when interacting with that object, will have that Doppler shift. Yeah.
I want to disagree with your statement that if you have a moving object, you can consider it as a static scenes, like sampling that, because you're not considering Doppler shift and this kind of stuff. So how do you account for that?
Yeah. So the most realistic is still if you have a car moving and you have a user moving, you'll have to consider both of them moving, and you have to ray trace multiple times with all the updates in your scene. But if you consider just buildings, not non-moving buildings, like buildings usually are, and you just have a user moving, then you can consider still the user speed in the channel that you are computing. Does that answer the question? You can consider Doppler if you assume that everything else is constant. And but bottom line, are you willing to do the ray tracing simulations over and over? Is that worthwhile? Or if you only want to consider the user moving across buildings, you don't need to actually ray trace multiple times.
Yeah, so I think we kind of haven't seen something like benchmark to see, okay, if I'm simulating this room, I put some receiver and transmitter in this room, then how accurate is the simulation with the real estate? Or do you have some benchmark on these kind of things or anything?
I don't know if we need those benchmarks. I mean, if we maintain everything else the same, I guess the question is also related to what ray tracing. In ray tracing, you have deterministic channels for a reason. If nothing moves, in theory, your channels should be the same apart from noises and those variations. So if nothing else moves in this scene, your channels will be realistic by just adding the Doppler and by sampling different positions. And by the way, in DeepMIMO, you can also interpolate between positions. So that gives you all the intermediate samples that then you can use for channel prediction or something that requires a finer grid of samples. Maybe we can continue that one afterwards. I feel like we'll have to discuss a few more.
Yeah, thank you.
Thank you. Oh, there's another.
Very briefly.
Oh, so nice to have all these questions.
Hi, I'm Bibor. I'm a PhD student at NC State University.
Yeah.
So my question is, does DeepMIMO have support for non-terrestrial networks like satellites?
If you ray trace that, it has support.
No, because there are several challenges when we consider satellites. Because one is like we cannot consider point transmitters because that would be the accuracy in the there is one parameter I forgot in ray tracing that that would make the execution time very large for long distance simulations. And the other problem is like there is atmospheric refraction, which is not considered in terrestrial networks, but is relevant in long distance travel.
Okay. So that does help answering the question. If you do need more complex channel equations, DeepMIMO uses the geometric channel equation. It does not account for atmospheric effects that are not already accounted for in the ray tracing. So in that sense, the channel equation currently is fixed. But besides that, any ray tracing simulation you do, it is technically supported in DeepMIMO. But you do have to pay attention to these approximations that you might be doing. Yeah.
Thank you, João.
One more? Whoa.
Well, maybe in the interest of time, because we're already over time, we do the rest later. Otherwise, it will be also unfair for the next speaker. Thanks a lot.